Section 3.6, Numerical Integration. We're going to first discuss the midpoint rule, which is just the Riemann sum. Okay, remember what the Riemann sum is. The Riemann sum is you take, say, if you had to calculate the area under the curve, we slice, say this is the area I want right here. So we're going to slice it into a bunch of rectangles. Okay, that's not a rectangle, but we're going to draw it across, etc. You slice it into a bunch of rectangles, and then each one of the width is called delta x, right? And then the length is just f of x at the point I. This is xi and stuff xi. And then you add it all up, and that's the area under the curve, except it's just an approximation. The more you slice it, the better your approximation gets. So then, so the midpoint rule means that the xi you choose happen to be the middle of your rectangular strip. So here's the midpoint rule. Okay, the midpoint rule, yeah. And I'm not even going to write it down necessarily. Yeah, the midpoint rule, as you see on the page, is just identical to the Riemann sum, except that you're calculating stuff the height at the midpoint. The reason to calculate the height at the midpoint is because it might be more accurate. Okay, instead of calculating at one end, then you're missing some of it. If you calculate at the midpoint, chances are it's either the average or close to the average, so it gives you a better estimation. So that's the midpoint rule. And so flip the example 3.39, which shows you how to use the midpoint rule, which is identical to how to use the Riemann sum. You just slice it into a bunch of stuff, figure out where the midpoint is, and then multiply each rectangle, right? Add it all up, and that's your estimation. So please do example 3.29 as your homework. Next, let's skip 3.40. Okay, we don't care about the arc length right now, and move on to the trapezoidal rule. The trapezoidal rule is very similar to the midpoint rule, with the only difference being that you are calculating, instead of a rectangle, we're gonna upgrade ourselves to calculating the trapezoid. That is, normally we do a rectangle, right, for the Riemann sum. So instead of a rectangle, now we're gonna do this. Okay, and join these two ends together. So then now this thing is a very long, thin trapezoid. And then we're going to calculate the area of each trapezoid, and keeps going that way. Okay, the purpose of the trapezoid rule is that we're hoping for a better accuracy. So when you do that, then you can see what happens is something like this. See? Then it looks like it's more accurate, but unfortunately, as it turns out, the trapezoid rule isn't any more accurate. In fact, I think it's less accurate. Nevertheless, we're going to learn how to do it. To do the trapezoid rule, we pull out the old rules of how do you calculate the area of the trapezoid. The area of the trapezoid is the top, okay, times the bottom. Plus the bottom, sorry. The top plus bottom times the height, okay, divided by 2. That's the area of the trapezoid, which translates into this situation, becomes this height is f of 0, x0 or something. Yeah, if we call this x of 0. Okay, so f of x0, that's this height, plus the other height, 0, is x of 1, is the other height, f of x1, and then top plus bottom times the height, which is your little height here, which is delta x, times delta x, and of course the whole thing divided by 2. And then you add this whole thing up, okay? Each one, then you slice it a whole bunch of thin trapezoids. They're strictly speaking trapezoids. You add it all up, and that becomes your new Riemann sum. Or kind of. This is Riemann sum by trapezoidal rule. I don't even know if they call it Riemann sum here, but the idea is the same, right? It's just not adding triangles. Instead, you're adding trapezoids. And then, so the trapezoidal formula, look at the next one, which is, well, because you have to add this and that one, and you continue doing that, see, the next one you will add fx1 and x2. So each item get added twice, except for the very first one and the very last one. So the formula end up looking like this. Okay, you have a big long formula where yeah, you see, you add with the area is fx0, and then you add it to x1, and then from x1 again to x2 and x2 again. Finally get to x minus 1, xn minus 1, and then from then one, that one goes to xn, and you don't have to repeat xn. So the first item and the last item is not being repeated. Okay, all the things in the middle, you have to have two of them. And with that, then as n goes to infinity, then that approaches your area under the curve. Unfortunately, the trapezoidal rule is, you would think that it's more accurate than the midpoint rule, but it's not. So yeah, and we're gonna, but first let's see you do one of the trapezoidal rules, which is example 3.41. Please do that for your homework. Next, let's look at the concept of absolute error versus relative error, which is on page 320. This is actually a concept that you already know. Okay, the absolute error is just the difference between the estimation versus the true answer. The relative error is the percentage. That is, how much is it off if you divide it by the original amount. It's like, are you off by 10% or 100%? Or 2000% or something. So the absolute value, yeah, that is, I'm sure you already know that. I mean, that's just something that was taught long ago, maybe 5th grade or something, when you learn percentages. So please do example 3.42, where you are told to calculate the error, whether it's absolute and the relative errors. The next example, 3.43, is also about calculating errors, which we're going to skip because, we're in calculus. We know how to do errors, for heaven's sake. So let's move on to something that's far more interesting. Look at the bottom of the page, theorem 3.5, error bounds. Now, what that means is if you have a function that's reasonable, it's continuous over a closed interval, and it also has a second derivative. That means it's differentiable all the way up to the second derivative, and then the second derivative happens to have a maximum. So that's quite a bit of requirements, but it does. Okay, let's say it does. I mean, in that case, what happens is that the error of the midpoint rule and the trapezoidal rule that we've done recently can actually be calculated exactly. Okay, the error is gonna, in the case of midpoint rule, is m times b minus a. B minus a is the range of that thing that you're integrating. And then the similar over 24n squared, and the error in the trapezoidal rule is a similar formula. But notice this, that let's see, yeah, you notice the two errors are very similar, except that the error in the trapezoidal rule has a smaller denominator, which means is twice as big. Okay, it's up to twice as big. If this error is a less than relationship, so the error might be 0. It's just that the error is no bigger than that value if you calculate it, which is quite impressive. That the error in the midpoint rule is far easier to do, right? And actually, it ends up being roughly speaking, twice as accurate as the trapezoidal rule. Well, at least the error is. Okay, the error can be calculated to be the trapezoidal rule is much worse, which means, and being the trapezoidal rule is slightly harder to calculate, no, I don't know, maybe we should just skip it or something. But maybe there are times that the trapezoidal rule works better. We don't know yet. So then the next problem is, now that we know the error tolerance, what value should we, then it gives us a way to figure out how many slices to cut to keep the error under allowed limit, okay? Which is just basic algebra or something. So please do example 3.44 for your homework. Next, let's look at the Simpsons rule on page 322. Now, the Simpsons rule has a very neat new idea. Now, so far, we've been approximating area under the curve with some kind of straight line. This is just a basic rectangle, and that's a straight line, but it's slanted. So it looks slightly closer. Didn't turn out to be better, but it looks better, right? But here's the Simpsons rule says, let's not approximate this thing with a straight line. The straight lines are not that good, right? Because your curve is probably not straight. So let's approximate it with a curve. Specifically, let's approximate it with a quadratic function. So we'll choose a quadratic function that happens to go through these 2 points. And being the quadratic functions can bend, right? So that should make an even better approximation. So that is the concept of the Simpsons rule. Now, of course, to draw a quadratic function across here, it's not going to be near as easy to do as a straight line, right? So that's what. So then, so in order to draw that little quadratic function, that is the parabola, we just a very small part of the parabola, we have to do something like this. So we have, say, the original function here, which is, I'm going to draw it over here. So we have an original function that goes, I don't know, I'll draw it the same as before, something like that. And then we have, let's say, 3 points so far, okay? For starters, we'll start with just 3 points, and then we'll increase it to as many points as we want. But first, let's start with 3 points. We'll call it x0, x1, and x2. Okay, and then, of course, if it's x0, then this point here is f of x0, right? And so on. This point, the y value is f of x1 and f of x2. Okay, now we are going to draw something, the quadratic function, where it will go something, quadratic function that goes through, let me see. Yeah, goes through all 3 points. That is, well, maybe something like, I don't know, this. Okay, this is a quadratic function. The approximation function, we'll call it px. The approximation function will be a quadratic function called we'll call it ax squared plus bx plus c, being the bx plus c, being that it is quadratic, it has this particular format, and also, but we don't know what a, b, and c are, so we need to, figure that out. And we're going to figure out what a, b, and c are going to be dependent on what the value of these 3 points are. They are coordinates, okay? Once you plug in the three different coordinates, you will be able to come up with crank out all 3 values. And the way you're going to do that is by these 3 formulas. So you're going to draw 3 simultaneous formulas like this, okay? Now, so oops, why did this thing suddenly turn around? Okay, okay, so you see, you plug in f of x0 is equal to px0. So you plug in x0 into your formula, similar for x1 and x2. And when you do that, then you have 3 formulas with 3 equations, right, with 3 unknowns. And what is that called? Simultaneous equations. And then you remember how that is done? If you take the determinant and then it's a matrix, and eventually you come out with something that was taught in pre-calculus or algebra or both. And so I'm going to copy these 3 formulas down on the board. Okay, now these 3 formulas all look very similar. Okay, you're just substituting x0 by x1 and then by x2. The purpose of the formulas is that we want to figure out what a, b, c are. They're numbers, and we need to come up with it in order to come up with p of x. P of x is the approximation, quadratic approximation of f of x. Okay, and then once we figure out what p of x is, then we can approximate our f of x in this tiny little area. And you notice that the reason we want to use a quadratic equation is because we might not know how to integrate f of x. It might be some weird hard function, but we do know how to integrate a quadratic equation, right? So then, the quadratic function. So that's all we need to do. And at this point, you might think, that's all we need to do. That's just one slice. And you have to find A, B, C in a 3x3 matrix, and you have to do all this stuff that you learn, and it's a complete pain, right? And it's like, what kind of, that is going to wear me out. And no, you don't. It's not going to, okay? Because in Simpson's rule, we're going to calculate these things, the P of X, but we don't have to do any of A, B, and C at all. We don't have to calculate any of it, which is, we don't have to worry about what ABCs are because they disappear in the calculations, which I will show you in a minute. So the Simpsons rule is rather magical that way, right? And so let's continuing, and we will keep looking. So here's a small piece of detail that is x2 plus this number plus that number is equal to 2 times this number. That's because of an average or something. Yeah, x1 is the average, okay, because it's smack in the middle. So x1 is the average of x2 and x0. So then here's a fact that says x2 plus x0, it happens to be equal to x1, 2 of them, okay, being that thing is the average. All right, now having said that, let's turn the page. So now we have all these facts at our proposal. What is the original integration? So originally what we were doing is trying to integrate from x0 to x2, right? That's our original integral, which x2. Okay, now the original integral, which we are now approximating with a quadratic function, which is called P of X. Here's our P of X, and the problem is we haven't done solve the simultaneous equations yet, and we sure don't want to, because there's a lot of work. And that equals to, so we're gonna write that down, which is what? Which is, of course, we'll plug P of X is this thing, so we'll write that down. Yeah, 0 to 2 ax squared. Okay, so I will write that down. That equal to from x0 to x2. Let's see, where to go? Ax squared plus bx plus c. Now you might say, well, I thought you said that a, b, c are going to disappear and it's not going anywhere. Well, that's true, okay? But we will have some patience and see why this is going to work out. So we are going to integrate this thing. Right now, we're just doing from 0 to 2, so we'll integrate one of them, okay? Like I said, the reason we're doing the quadratic function is because it's so much easier to integrate than the other one, which might not be possible to integrate, no matter how many tricks you pull out your sleeve. So we'll integrate this thing with the quadratic formula, and that gives you, that of course gives you the good old integration formulas. That will be a over 3, x to the power 3, power rule, okay, be x power 2 divided by 2, and then plus c just multiplied by x. And then we're evaluating this thing from x equal to, from x, from x0 to x2. And of course, ABC is still there, but no worry, it'll be gone soon, magically. Okay, so now we got to this point, and well, what about it? At this point, I want you to do your homework, okay? From this point all the way to the let me see, where do I need you to end? Yeah, this, okay, all the way to the end. I mean, in the middle page. Let me show you. We are right, where are we? We are right here, right? I want you to do all the algebra from this point on and all the way down to here, okay? Where everything is sorted out and you multiplied and squared and stuff like that. And then collected terms and all those things, okay? It's important. The reason I want you to do that is because this kind of stuff is, there are a lot of symbols here. You have x2, and then you have x0, and then you have the third power, and then you have ABC. It can look confusing, But if you do it one time, or more, if you can't get the right answer, that's probably because you, I don't know, wrote a symbol wrong somewhere and added x1 with x0, that kind of thing. But it's a good practice for you to navigate through all the symbols and do some basic algebra. Okay, and despite no matter how many symbols there are here, it's still just basic algebra. So that's why I call it that. So please do this thing all the way to the end as part of your homework. Now, there are so many symbols here, as you can see, there's a good chance that you might mess up before you get to the end, and then you can't get the right answer. If that happens, just do it again, okay? If you do it enough times, you should be able to get the right answer. And anyway, so we got to the end, which ABC is still there. Now what? So if you work on the pack of algebra very, very hard and not make any mistakes, might have to do a few tries, then you eventually get to this thing down here, will eventually become that thing, okay, as your book shows. And at the end, you will come out triumphant as looking like this, which is fine, but as you notice, A, B, and C are still there. Now what? Okay, now what we're going to do is use this. Remember, x2 plus, what is that? I think should be 0, okay? We said that in the previous page. Yeah, x2 plus x0, one of them is 0. The point is, I'll just write it down here, okay? Now, x2 plus x0 equals to 2x1. Oops, why did I say I there? See, I can't even write this down without messing up. Imagine going through that. It's like in for it. Okay, x1. So then what we're going to do is plug this fact in here, okay? And see, there's x2 plus x0 right here, right? And again, x2 plus x0 right here. So we're going to plug it in and then rewrite the original equation down, continuing. That becomes delta x over 3. The first two are fine, f of x2 plus f of x0. And then plus, what is that? We have A. I'll write it down here. Let's see, give me a second here. Now, before I go forward, I should mention that the original equation that you were supposed to do only have A, B, C in it. There's no F in there. So how did this F get in? Now, don't forget that what happens is that F of x2 and x0 is these two things, which does have that in there when you evaluate. So you will substitute it by these equations, okay? You have a bunch of things like that and a bunch of stuff like that, and you substitute it accordingly. And that's why the fx2 and fx0 suddenly showed up. Okay, so having said that, let's continuing this part with this condition, x2 plus x0 is equal to 2x1. See, here's x2 plus x0 here. So we will add that up. I'll write it on the second line. That is equal to 2x1, okay? And then squared. And similarly, plus 2b, that's again 2x1. And then plus 4c. C, that's a C. All right. And at this point, you notice what is this? This is the same as 4a x1 squared plus 4b x1, right, plus 4c. Now, how neat is that? This is exactly x1, f of x1, see? Because, I mean, yeah, f of x1 is the one with the ABC with x1 in it. So this is equal to f of x1. And that's where, sorry, why do I keep writing I? But the point is, this is how ABC disappeared from the Simpsons rule. So we're supposed to calculate ABC and do the stuff, but the way the algebra worked out, you don't have to. It's just f of x1, which is great because then our life is so much better. Okay, so then the integral of the approximation end up being, we'll rewrite it here, which is delta x divided by 3 of f of sorry, this is 4, right? There's 4 of them. Yeah, there's 4 of them. Don't forget the 4. See, there's 4 of them. And then, so delta x divided by 3. So we have x2 plus f of x1. I will write down the 4x1 first. 4x1, 4x1, and then plus the last one, f of x0. All right. Okay, the book, I think my note says the book has a slight mistake here. What's the mistake? Oh yeah, this thing's missing a C, where it tells you the substitute f of x1, right? Look down here, f of x1 a plus b, see, the C is missing. So go ahead and remember there's a C there, add that in. And then what was the other problem? Also, there's some integration that, okay. So the next thing we are going to do is the integral, so our original integration, which is approximate. No, actually, let me see. So what was this again? Okay, after all this algebra, we forget what we're doing. Then remember that this is the integral from x0 to x2. Then actually it's an approximation only. Okay, that should be the approximation sign. But you get the idea. We're approximating. So the approximation of f of x from x0 to x2 is f of x is roughly this delta x times this stuff. Okay, now we have now we'll do the next step. Okay, we'll go from x2 to x4. Now x2 to x4 then is the same. It will be a similar formula. So if we integrate from x2 to x4, okay, and then the formula will be identical, except that this will be x4, and this number will go down to x3 and then x2, but otherwise it's identical. So and again, there's a slight mistake in your book that it says when we integrate from x2 to x4, right here, around here, where you see, okay, then it equals to the thing added up, but somehow in the next line it says x0 on the bottom limit. So it should just read x2, okay? Yeah, and that'll work out. So that's a small typo. And then the next line really is x4. So then when you integrate from 0 to x4 and you add up these two equations, then you end up with a longer thing. Now, the longer thing looks something like this, okay? If you end up integrating from x0 to x4, then you end up with the whole thing. It end up being, you have f of x0, then you have the 4x1 and 2x2, and then 4x3, and so on. You follow that pattern. So eventually, the Simpson's rule then come up to be something like you see in a book, theorem 3.6, where you have you start f of x0, and you have the whole thing is going to be divided by 3. Okay, and then, well, because it happened to be that worked out that way. So you start with x0, then you go to 4, 2, 4, 2, 4, 2, until you get to the end. The last one is going to be 4 and then 2. Now, that one part that's important is that n has to be a positive even integer. That is not true with all the other similar Riemann sums that we did, but in Simpson's rule, because the way we developed it, you have to slice it into an even number of slices. Okay, because we have to. That's how we got it to work. So then, so other than that, everything should be just fine. So the Simpson's rule, as you can see, is that very interesting point. And while the addition is somewhat cumbersome, we don't have to do any of the ABCs. Okay, we had to do ABCs for each slice for like a couple thousand times of when you slice it. Yeah, that would that might even wear out a computer. I don't know, but we don't have to do that. See, it magically come out very nicely. And so that's the Simpson's rule. And the Simpson's rule is approximating by a curve rather than a straight line. And as a result, it's more accurate. How much more accurate is that? Now let's look at the next page and look at the Simpson's rule's accuracy. The Simpson's rule is the accuracy is look at the error estimation for the Simpsons rule. See, the b minus a is higher power, but look at the denominator. The n is being raised by 4 power. That's a lot. And then you divide by something like 180. Rather, the other one was what, 12, 24, something like that. So the Simpsons rule is likely superior to the others. And although it is, of course, you have to do the 4 and 2 and, well, I guess I didn't write it down, but you have to do 4, 2, 4, 2, and then eventually 1, 1 at the end. So it's slightly more cumbersome, probably. But it does, you can see why it will work better, because you're approximating with a quadratic function. So the Simpsons rule, while it's slightly long to explain, is not hard to apply at all, but it is, like all Riemann sums, it's tedious. So please do example 3.45 where you try your hand on this using the Simpson rule. So for homework on page 327 for this section, please do problems 299, 301, 329, 344, 45, and 46. Now, the last few problems, at least 2 of them, I think, are multiple choice problems, which I wouldn't have assigned them, but I was so surprised to see a multiple choice problem that I had to assign it for you to have some fun, I don't remember ever having multiple choice problems in homework in calculus, but there you are. So, okay, and being that these homework are very straightforward but tedious, I am not going to go over them. You shouldn't have any trouble, I don't think, getting to the right answer. Just follow the rules and everything should come out. And being that I'm not going to go over the homework, I do have the answers for the even number problems written down under the video. So you can check that. Well, at least that's what I think the answer is. And well, this should be pretty good because I only pay, the answers are just for those funny multiple choice problems. Anyway, so and today I want to start my literature recommendation for my class I mostly studied majored in math, but I also as a sideline I focused on literature. Okay, I do a lot of reading. And one book I would recommend that you read is the Autobiography of Benjamin Franklin. Benjamin Franklin is probably the coolest guy in the United States history. He is, of course, you can think of the first one. The absolute coolest guy is is George Washington, of course, but Benjamin Franklin, however, is extremely neat. And you will know that if you read the autobiography of Benjamin Franklin that he wrote himself, of course. The one reason I want to recommend it is Benjamin Franklin actually helped with teaching girls mathematics in the United States. At the time when the United States was founded, they were not really teaching girls math. Well, they were hardly teaching anybody anything, right? Because everybody had to make a living, and since they were kids. But Benjamin Franklin said that he told an experience. Well, actually, from this point on, there's no more calculus, so please feel free to stop watching if you need to, get your homework done. And anyway, so I want to talk about Benjamin Franklin because in his promotion of math for girls, teaching math to girls, what happened to him is that Benjamin Franklin, when he was young, he was he was poor, and then he worked hard, and then he owned his own business, and when he was in his 40s or so, he retired, and then because he made enough money. So after he retired, he invested his money with various people that want to start their own business, and he think they're a good risk to invest with. So there was this one guy who was an excellent risk, great guy. Uncle Ben trusted him completely. So he invested with the guy a sum of money, and the guy was doing great. He started his own business. He was able to make payments. But then one day, the guy just had a heart attack or something, and up and died. Okay, nobody saw it coming. Guy's young, healthy, everything. And not worse than that, the guy left a young widow and a very young child, 5 years old or something. So Benjamin Franklin thought, oh no, he said Franklin is a great guy. Right? He would not go try to take the widow's coat to get the money back. Not to say it would do any good. There's a big sum of money that a coat is not going to pay off. So he thought he might as well kiss his money goodbye. To his surprise, however, the young widow and the young child, just the young widow, she took care of her child and she continued taking care of the business, okay, and kept running it and continued to make money. She made enough money that she continued to make payments to Benjamin Franklin, didn't even miss a lick. He was most impressed, right? So one day, well, even back then, men and women didn't really have that much communication, right? But Benjamin Franklin specifically asked her, may I ask how you know how to do this? She kept all the accounts and how do you know this math? Because this is complicated math of a business, and how do you know how to do this? And or even to calculate how much money to pay me. And she says, I'm from Denmark, I think she said. I could be wrong. It's one of those countries, Northern European countries, the way I remember it. I'm from Denmark, and in my country, young girls are taught math as well. As a result, I do know how to keep accounts and keep our business going. And Benjamin Franklin was most impressed to hear that. Now, eventually, the woman continued to make payments, and then when her kid was old enough, maybe 11 or 12, which is defined as old enough back then, right? She came to Benjamin Franklin and offered to buy out his share. Pay the whole debt off so that she can have the business for her son. And Ben Franklin totally accepted. Oh yeah, no problem. So he got all his money back plus interest, so years later, when Ben Franklin was at the United States Convention after George Washington kicked the British out, okay, and then they were talking about what to do with education, and they were saying, no, we don't need to teach girls math, right? I mean, what's a waste of time? Girls don't even know math. But Benjamin Franklin then repeated this story and says, we really need to teach girls math. That way, if something happened to their husbands, there's a chance they can support themselves and not become a burden of society. And so the whole rest of the convention heard that story, and they agreed. So then, from then on, the United States teach girls math as well as boys. Now, isn't that a neat story? So yeah, so that's the end of. That's one reason I want you to read the autobiography of Benjamin Franklin.